Hello, and welcome back. Let's continue our class of Eurocode 2. We are going to proceed with chapter number 1, section number 3, I think. We did last time the basic data, okay? And this time is section number 3, actions. These actions means we have to evaluate the forces acting on our building, okay? Vertical and horizontal forces. So for the vertical forces, it will be mainly the permanent load of like self weight of the building itself and imposed load and other loads due to maybe exploitation of the building. And the horizontal, in this case, will be mainly from the wind, okay? We will try to evaluate the action on the wind, of the wind on the building. So this will be like the middle of this chapter, actions. So as you know, actions, Eurocode is not from Eurocode 2, it's from Eurocode 1. Everything related to the actions, related to the forces acting on structures is from Eurocode 1, not Eurocode 2 actually, okay? And the first video of this program, I talked about that. So Eurocode 1 also is divided in many sections, okay? The first section, the first part of Eurocode 1, okay, is about density, self-weight, and imposed loads, okay? Section 2 is about fire actions, okay? And section 3 is about snow load, because you have to know what is the load of snow and how you apply it to the building. Section 4, which we will partially use in this video, is about the wind load, okay? You have to know, depending on the speed of the wind, depending on the location, the area, the category of your building, category of the area, what is the power of the wind. As you know, wind is horizontal load. It's very important. In some country, we have also earthquake, but earthquake, as I said, not all countries have earthquake. So this wind will be, in that case, the main horizontal load that has to be evaluated in the design of the building, okay? So due to the limited dimension of the building, thermal action were not considered. It means we will not consider this fire, will not be considered, and also the action of explosions will not be considered in this design in our case, okay? But it doesn't mean that in these actions don't exist, okay? Fire and explosions actions, okay? If you want to design a building so that it can resist some explosion, you have also to refer to Eurocode 1 and evaluate the actions of the explosions, okay? So we will be mainly this one, self-weight, density, and imposed load, obviously. And we will use also snow load, and we will use also wind load, okay? So if available, gamma partial safety factor are taken as what we suggested value in Eurocode 2. This, please understand that it's not the actions, because we have the load the value of the load is affected is multiplied by a partial factor, okay? Partial factor like gamma 1.5 for maybe, let's say, a permanent and non-favorable action, 1.5. These are the partial factor I'm talking about, safety partial factor, okay? If the load is has this certain value, you take that value and multiply it by the partial factor. So these partial factors are coming from Eurocode 2, okay? Only the value, we need to know the value of the action, and these value of action are coming from Eurocode 1, but the partial factors are coming from Eurocode 2, okay? A little bit, okay. Let's go and talk first from start from self-weight. Self-weight, as I said, the gamma partial factor, non-favorable, 1.35, for example. 1.5 is, yeah, mainly for variable, not permanent, okay? Sorry, 1.35 for permanent and non-favorable actions, for example. So for concrete, the weight, 25 kilonewton per cubic meter. For example, this value, for example, of self-weight is normally from Eurocode 1, but this partial factor is from Eurocode 2, okay? So the clay element, if you remember the previous lesson, in the previous video, we said that there are these clay element embedded in the slab. So these element have this weight, okay, according to Eurocode 1. Okay, then this is for self-weight. Self-weight category, it is permanent load, and category J1. And we have what we call category J2. Okay, permanent load, category J2. But finishing, pavement, embedded services, and partition. Okay, these also are permanent load, but as you can see, the value are not that how to say. These are the main permanent, if you can say that. That is the body of the building itself. Okay, these are maybe just to make the building beautiful, more beautiful. Okay, so all these, Eurocode 1 is telling us that this is the weight we should consider. Okay, but the partial factor for this, of course, Eurocode 2 is suggesting this value. Okay, for wall on external perimeter, window also is included. We have this value of the load applied on like linear meter, not square meter. Now, variable actions, variable loads, the load that are not constant, depending on the period. We have first the partial factor, which is 1.5, suggested by Eurocode 2. Okay, but the amount, the value of the actions themselves are this kind of thing, this example. Okay, for living, people are living there, as we said, we consider this 2 kilonewton per square meter. Okay, for these stairs, office open to public, sorry, 4. For snow, 1.7. For parking, 2.5. So as you can see, these values are coming from Eurocode 1. And then this factor, these are what we call like combination factor. Okay, and we will explain this soon. It's like when we will explain when we use each of them. Okay, but the value are here. It's like when something is not permanent, as you can see, it's variable load. It's not permanent. Okay, we have to ask ourselves the frequency of the load. Okay, is it this load is not permanent? So how often this load is happen to be applied on the building, on the structure? Okay, that's why we have to multiply it by some factor to consider that frequency. It's something like that. Okay, so you will see that maybe for ultimate limit state, we will apply this. It means you will not consider this value since this value is not permanently applied on the building. Okay, like if we take example, snow. Snow is not permanently on the building. Sometimes sun come out, snow melt, or some country there is snow is maybe just 3 months. It's not permanently. So depending on where you are, you need to apply this. For example, you see half 0.5. Okay. It's true that snow, the weight of snow, for example, is 1.7 kilonewton per square meter. But this weight is not permanently on the building. How often is it applied? Maybe 0.5, 50% of the time. This is the meaning of this value. Okay, I will explain more this value. So let's keep them here. Okay. So for operating load, climate load, snow, wind, this kind of value, we call them like the representative value are set according to the frequency, that's what I was saying, duration of the load of application, and the nature of the combination, okay, in which they occurs. We have, for example, this one, this QI is the value of the action, nominal value of the action, like this value, okay? This is, it can be, the value is changing, okay? I, now 0, like this one, I think this is C0, for example. This is exactly 0. This one is combination value when you want to combine load, because as you will see soon, we have to combine permanent load and variable load to obtain the design load. Okay. Frequency, this is 1. Okay. It's not here. We don't need that here. And this 2 is exactly this one. This is quasi-permanent value. Okay. Let's keep them here. So the coefficient 0, which is this one, we use them in fundamental combination. For example, ultimate limit state, you have to use this one. Okay. It simply means that if you want to design according to ultimate limit state, you have to multiply this value by this, and that will make the value of the action, and then multiply again by the partial factor, which is 1.5 for variable actions. Okay, so this one you have to take it, and in also rare combination, which means service limit state, coefficient 1, which is not included here, is accidental combination. Accidental combination can be earthquake, for example, or impact. For example, a car can come and hit the building, for example. This is accident. Okay. Number 2, these are here. These are used also in accidental combination and for seeking the shape stability. like the formation of the building, it is just about serviceability limit state. Okay, we will see also how to use this. So I will give some example for fundamental combination. For example, here is an example. Okay, you can see here 1.35 is the partial factor for like permanent category 1. We can say uh, the first one, self-weight, this kind of thing. Okay, can be used for this. And this one is also permanent load. It is here actually. Non-favorable and permanent actions. For example, the self-weight, okay, of concrete, self-weight of this embedded clay element, okay, the two phase. And this G minimum, G minimum is like in case of favorable and permanent action. It is permanent, not variable, it's permanent, but it's not non-favorable, it's favorable action. So this is in this case. Okay. So in many cases, this one is absent, but it's not always absent. You have sometimes some loads that are permanent, but are also good, helping to support. In that case, you don't affect them by, you don't multiply by the partial factor. This partial factor, 1.35. Okay. And this one is variable action, and it's called like the leading one, leading or sometimes basic, leading variable action. It means maybe the most important one in the variable actions, the leading one, okay? And multiplied, as you can see, by 1.5 sometime, which is the partial factor, okay? Gamma Q1. Here, this one, you can see, this is gamma G1 or gamma G. Okay, then comes this one. This, as you can see, it's these ones, variable action that are called accompanying actions. Okay, different to this one, principal. This one like variable action, but principal one. This one are variable actions, but they are just accompanying. And these 0, 1, 2 here, this is what we discussed here before. Okay, C1, C0, C1, C2 is what we discussed. But in this case, it just P1. It is used for fundamental combination, mainly for ultimate limit state. C0, sorry, I said one, it's 0, this one. Okay, 0, and this I, okay, can change from 2, 3, yeah. So this is just the different one example of combination. Accidental combination now, in case of accident. Then you have this. You can see that there is no partial factor here, J maximum. This J maximum is similar to the previous, that defined in the previous slide. You have J minimum. And FA now, this FA is nominal value of the accidental action. For example, if a car hits the building, you will have to evaluate the force of this car. For example, depending on the speed and the weight of the car. Okay. And this one, this 11, Q1 is the frequent value of the variable action. And these are exactly what we have here. Okay, this value, it is here, quasi-permanent value of another variable action. So in case now of design of serviceability limit state, this is what we have, the combination you have. You can see that it is similar to the first combination in the previous slide, the combination in the previous slide, but we don't have partial factor here. Before it was 1.35 here, and here it was also gamma q. We don't have it here. So in case of serviceability limit state, it look like we don't have partial factors. We just have the nominal value of the action of the load. And this one is the one here again. Okay. So all this just to tell you why we need this combination factors. Okay. Please know the difference between combination factor and partial factor. They are not same. So let's go now for the wind action. Maybe this is the core of this lesson, this video. How to evaluate the action of the wind. This is normally, as I said, from Eurocode 1, not to Eurocode 2. Okay. How to obtain the value of the force, the power of wind. So first, the combination factor, the combination factors for this are this value, C0 and C2, same as in the previous slide in the table. Okay. Next, in case of wind, as I said, you need to consider the type of area where your building is located. In our case, in the previous video, previous lesson, we said it was in terrain category 4, okay? And it is not close to the sea, and it is at 300 meters above sea level, okay? So if you go in Eurocode 1, you will find this kind of table giving you terrain category, okay? Category 0 is sea or coastal area exposed to open sea, okay? Okay, you can read by yourself, I think, but we will go to this category number, terrain category number 4, which is our case here. This is area in which at least 15% of the surface the surface is covered with building, and the average height exceed 15 meter. Okay, this is what we have for this category. So it means it in area where there are many other buildings, okay, because the surface is covered with buildings and the average height of this building exceed 15 meters. Okay, so in that case we have Z0 1 meter, Z minimum is 10 meter. What is Z0? What is Z minimum? Especially the Z minimum is very important here. Okay, this Z minimum is the height below which the wind power is considered to be constant. Okay, the wind force is considered to be constant in this, but above that, above the 10 meter, the wind power is increasing by when the height increases. Of course, if there is Z min, it means there is Z max, right? But in Eurocode 1, Z max is 200 meter, okay? 200. So in our case, our building if I remember it, around 19 meter or something like that. Around 20, 19. Okay. So these two values are very important for us. We have to consider them, Z0 and Z min. Okay. So considering that and referring to Eurocode 1, section 4, if you remember, we said section 4 was about wind. Okay. Section 1 being the density, self-weight, and so on. Okay. Section 4, the beginning of this video, I said it is related to wind action. So if you go in Eurocode 1, section 4, you will have the following. Okay. Basic wind velocity. This is the formula to obtain the wind velocity. You will see where we need to apply this wind velocity soon. But first, we calculate the wind velocity. Okay. So these two coefficients are used to obtain the wind velocity. In our case, these two are equal to 1. And this 0 is 30 meter by second. This is the speed of wind. Okay. In this category, we are. So if it another category, you have to, it is different, but these values are given by Eurocode 1. Okay. So if your case is not in the same category of building, you may have different, not category of building, but category of area. Okay. In this case, it's urban area. So the wind speed, basic wind velocity is this. And then you need the category, it's already given, right? We have Z0 is 1, Z in the previous table. Okay. So this wind speed, basic wind speed, maybe it depends on each country also. Please check. And terrain factor, this is depending on this terrain category. Okay. It given by this. You see how we use the Z0 now? The Z0 is used to obtain KR. This is the formula. And we will see also where we need to use this one, but just follow step by step and we will reach there soon. Okay. So use this formula, replace this Z0 by here. And as you saw in the previous slides, this Z0 depend on the terrain category. Okay. So this is what we have as value of KR. So where do we need to use this KR? Why do we need it? Okay. Orographic factor. These are C0, it is 1. Okay. Turbulence intensity. Turbulence intensity is given by this equation. KL is 1 in our case. Okay. So it will be just 1 divided by this Z, ln Z, logarithm of Z divided by Z0. This Z is given here. The Z minimum, sorry. This Z0 is here. Okay. And the Z is just the height when you go up. So now we have this C0 and we have this IV, turbulence intensity. Okay. This value is a given value. So we can calculate now exposure factor, CE. And this one is using the turbulence. Okay. For Z, less than 10 meter, it means below 10 meter. Okay. Below Z minimum. This formula is giving us the exposure factor. Okay. The KR, we calculated previously. I will go in the previous slide to show you. KR and C0. And this one, previous slide, this one, okay, C0, we obtain this here according to Eurocode 1 for this building, okay, and this KR is here. We calculated this here also. And this IVZ is 1 divided by ln Z bar Z0, okay? So we need this one and this one and this one, KR, to obtain the exposure factor, okay? Like this. See, KR is here, C0 is here, and this one. So below or at 10 meter level, this is what we have. We have this value, constant. It doesn't depend on like Z. We consider that it is this value, even below that value. And for Z higher, larger than 1, but than 10 meter, then this value is what we have. In this case, you see that it will depend on Z. It will depend on Z. Okay, this is a function of Z, function of the height of the building now. It's not a constant value anymore. But here also we need KR C0 and also this ln Z of bar Z0. Okay. Please wait. This 1 divided by this, it is just consider. So this is the minimum one, and this one is increasing with the height Z. And basic velocity pressure now. So now we have CE, remember that? We have CE for the two category, the two level, the minimum, and this one is maybe maximum if we can call it like that. So the pressure now, we are going for pressure. This one, basic velocity pressure. Do you remember the velocity we calculated? V, basic velocity, okay? It was 30. But anyway, 1 divided by 2, density multiplied by this velocity. This is just conversion. You have to convert the velocity, okay? And the density, it has to be converted so that you can obtain kilonewton per square meter in kilopascal, okay? So using this velocity, we can obtain this basic velocity pressure. It means if you have the velocity of the wind, you can obtain the pressure of the wind, okay? So the basic velocity we calculated the beginning, it was 30. So using this equation, we can calculate the basic pressure of this velocity. Then peak velocity pressure, not basic now, the peak one, it has to be obtained from this, what we estimated here, okay? See, if Z is less than 10 meter, we can see that the value of C here is this value, 1.13. So we have to use it here and just multiply it by this basic velocity pressure, okay? So it will be this one multiplied by this one. Maybe On this one, there is a mistake here. Let me check. Or maybe it's okay. Z less than 10 meter. We have to use this CZ. It is this one. And you just multiply this by this one, CZ. Okay. Let me check. Okay. I've corrected it. So yeah, we have to consider this one. CE for the value above 10 meter level. Okay. Multiply by this QB, the basic velocity pressure. Okay. Multiply it and you will get the peak velocity pressure for the level below 10 meter. Okay. This one, it is just this one, 1.13. Multiply by this and you will obtain the peak velocity pressure. Okay. This basic velocity pressure, this is peak velocity pressure. Then for above 10 meter level, and take this value, the basic velocity pressure, multiply by this one. Okay. The CZ, you are seeing CZ is this one. This is CZ. Okay. So you can calculate. That one is getting bigger when Z is increasing. Okay. So you can calculate, for example, the value for Z is 19, which is the height of our building, and you will obtain the value. Then we have to use this peak velocity pressure to obtain the pressure on the wall on the building itself. Okay. So wind pressure on external surface of the building, we have to consider this coefficient. Okay. If the direction is like this, the positive, this one is negative, but both are acting on the building. So you can see it can be in or out. This is just illustration, but use these coefficients are multiplied by the previous one, the peak velocity pressure. Okay. It is like we can say somehow partial factor or combination factor for the wind. Okay. In our case, for another factor you have to consider is this one, structural factor. Okay. If you're building like in our case, the framed buildings with structural wall less than 100 height, 100 meter of height, then this factor are considered as 1. Okay, it's not always 1. So in our case, it is 1. So it means like it's neutral factor. So these are not neutral. So you have to do 0.8 plus 0.4, because it will be minus 0.4. Okay. So then the wind pressure on the surface will be like this. This one is the one we obtain as peak, if you remember, peak velocity pressure of the wind. And these are the factor 0.8 and 0.4 minus 0.4. We add them together. And these are the structural factor, which we said it is 1, so it's neutral. So if we add all this, we will obtain 0.8 minus 0.4 multiplied by 1. 1 is this 2 structural factor. Then we will obtain just 1.2 multiplied by the peak velocity pressure. Okay, so if we do that, in that case, for Z less than 10, we'll obtain this value. This, if you don't understand this, it is just detailed for this one, QPZ, for in case of Z less than 10 meter. Okay, or if it's difficult for you to understand, just take 1.2 multiply by the peak velocity pressure of the wind below 10 meter. I will go back in the previous slide to show you that. Remember this value. Where is it? Okay, maybe we will take this value and we bring them to this one is 1.13. You replace this by this value. Okay. So if you multiply this 1.13, multiply it by this one, then you will see that you will be able to obtain a constant value for this one. Okay. So these two, maybe we'll take them. Just remember that the value for this one, C10, is 1.13. And CZ is this value, okay? This equation. Remember that. Let's take this to here. Okay. So you can see, if you take this, remember that this one, CE10 is 1.13 according to this one, 1.13. So if you take that 1.13, multiply by 0.563, okay, this one is the peak velocity pressure, which is here. In this case, okay, peak velocity pressure, QPZE minimum, this one. Multiply this one then by 1.2. You will see, you will obtain this. Okay, so technically it means take this value CE10, it is here, CE10 1.13. So 1.13 multiply by 0.563 and multiply it by 1.2. You will obtain this. Okay, this is the detailed equation formula. You can see that this is exactly what is written here. It is same. If you do 0.23 square, you will obtain this coefficient. Multiply by this, okay? You have to multiply by 1.2 also to obtain. So in case now of Z higher than, let's say, than 10 meter, then you have this value. It is same, okay? This, just remember that the key point, the peak velocity pressure multiplied by 1.2 is giving you the pressure on the surface, on the wall, okay? This is what you should remember. This is just detailed equation, and you can find it by yourself by replacing this z. When z is 19 meter, then you will obtain this value. This is kind of the maximum at the top of the building you are obtaining. So it's changing from 10 meter upward. This value is not constant, but from 0 meter to 10 meter, this value is constant. Okay. Then based on that, you can draw something like this. You can see from 0 to 10 meter, we have this value 0.77 kilonewton per square meter. See, from this is the face, main face of the building. If you remember, this is profile view, side view of the building, according to what we did last time. This one is side view. And for both, yeah, we have this. So from 10, it increasing like this. So it means this one is 1.04. And this one down here is 0.77. So one in this direction, wind in X direction, wind in Y direction. Okay. So normally, this will just give you, usually you use to obtain the value of this value directly like this without calculation. But now I am showing you how to calculate this, how to obtain this value. Okay. And this one is up here, but you should consider this equation. From Z is from 10 to 19, for example. Okay. So I think that's all for this time. We'll stop here. Thank you very much for your time, and we hope to continue this very soon. Okay. Okay. Thank you for your time, and see you soon. See you next time.